welcome to AP Chemistry. You guys are probably wondering how hard this course is and what to expect from it, and I was in your shoes about a year ago. First of all, I'd like to say that you must enjoy learning chemistry in order to excel in this course. If you don't like science or have a difficult time putting effort into it, you may be stuck in a harder time than the others. In this video, I'm going to talk about the very basics and foundation of chemistry that you need to know. It's most likely going to be the very first unit, so it's important to refresh your memory of these topics. This is going to be the table of contents that I'm covering today: mole conversions, balancing equations, stoichiometry, and limiting reactants. First, mole conversions. Most of you are probably aware of what moles are. They're the unit of measurement for atoms, molecules, and other extremely small particles that we deal with in chemistry. Converting moles from the number of molecules, atomic mass in grams, and vice versa are the most basic parts of this course. So let's go over it in detail. In order to calculate the number of molecules, we must use Avogadro's number. By definition, it's the number of units in one molecule of any substance, and it is equal to 6.023 times 10 to the 23rd. And its unit can be anything you're finding. For example, the number of molecules, atoms, ions, or electrons. Let's look at question 1. How many moles of aluminum are in 3.01 times 10 to the 22nd power of atoms of Al? We must use dimensional analysis to solve this question. First, we write the given information, which is the number of Al atoms, and we also know that there are 6.023 times 10 to the 23rd atoms in one mole of a substance. So if we calculate this, we get that there are about 0.05 moles of Al. The next problem, try for yourself and watch the video to reveal the answer. This is the answer. Next is the conversion of moles between atomic masses. Before this, I'm going to go over how to read and understand each diagram of the periodic table. Also keep in mind that the AP Chemistry reference table looks a lot different than the one you guys are familiar with from Regents Chem, and that there are a lot more concepts that you must memorize. The atomic number, which also represents the number of protons, is located on the top. For example, the atomic mass of oxygen is 6. Another part listed in the AP Chem periodic table is the atomic mass, and the atomic mass is the average mass of isotopes of each element. Isotopes are the same element with different number of neutrons. The total mass of each element is the sum of the masses of protons, neutrons, and electrons, but remember that electrons are extremely minuscule compared to protons and neutrons. Therefore, atomic mass is basically just the sum of protons and neutrons. Most obviously, the symbols of each element are also shown in the periodic table, and I recommend memorizing the names and symbols of at least the first 3 periods of the table. The Regents Chem reference sheet also indicates the oxidation states and electron configuration of the elements, but you must memorize them for the AP course. To find the atomic mass of the substance, add up the atomic masses of each element given in the chemical formula. Let's look at example 2 to convert moles to mass now that you have refreshed your memory on how to find masses of each element. What is the mass of 2 moles of CO2? First, we need to find the masses of 1 mole of CO2. In 1 mole of CO2, there are 1 mole of carbon and 2 moles of oxygen. Referencing the periodic table, we see that 1 carbon is 12.01 grams and 1 oxygen is 16.00 grams. So 1 mole of CO2 is 12.01 plus 2 times 16, which is 44.01 grams in total. Again, starting off with the given information, 2 moles of CO2, and in 1 mole of CO2 there are 44.01. Therefore, there are 88.02 grams in total. And again, the next one, try for yourself, and the next slide reveals the answer. Next is balancing equations. Knowing how to convert moles to mass and mass to moles, stoichiometry should not be that difficult, but in order to use stoichiometry to solve a problem, you must be looking at a balanced equation. Without a balanced equation, it's impossible to figure out the exact proportions of each substance within a given reaction. A balanced equation not only equips you with the tools needed to use stoichiometry, but it also gives you a clearer picture of the ratio between reactants and products. I'll explain the how-tos using an example. Until you're more familiar with balancing equations in your head, a good way to start is by using a chart, which I'm sure you guys remember from Regents. Given this unbalanced equation, we can first write out the elements involved in it, which are carbon, hydrogen, and oxygen. On the left side, or the reactant side, write the current number of each element: 2 carbons, 6 hydrogens, and 2 oxygens. On the right side, or the product side, there are 1 carbon, 2 hydrogens, and 3 oxygens. First, with the easy element, carbon, all we have to do is multiply the product side by 2 so that there are equal amounts on both sides. However, since we multiplied CO2 by 2, there are more oxygens as well. Before dealing with the oxygen, we can balance the easier one, hydrogen, first. We just need to multiply the product side by 3 to balance the 6 hydrogens on the reactant side. Again, H2O is connected with more oxygen, making it 7 oxygens rather than 3 that we started out with. To balance the 2 oxygens on the reactant and 7 on the product, we multiply O2 by 7 and double the rest of the equation. You know the drill. Try the next one for yourself. The third topic is stoichiometry. It's the calculation of quantity in a chemical equation, and it can be used to make predictions of the outcomes from a given equation. It tells us the quantity of each reactant we need in order to achieve the desired amount of product or the amount of products we have produced. Some of the ways that this calculation method can be used are as follows: to calculate how much product a chemical is expected to produce, to calculate the percent yield of a chemical reaction that failed to produce the product as needed, to calculate how much reactant is necessary to react with another element, to determine which of the two will be consumed first in a chemical reaction, also known as limiting reactant, and to determine the formula of an unknown compound. Here's an example of how stoichiometry is used. The reaction 2KLO3 produces 2KCl plus 3O2 is given. How many moles of O2 will be formed from 2.5 moles of KClO3? If there are 2.5 moles of KClO3, and for every 2 moles of KClO3 there are 3 moles of O2, there are 3.75 moles of O2 in the product. And last but not least, limiting reactants. An easy way and the most common way that this concept is explained is through cooking. Imagine you're baking a batch of 10 cookies and the ingredients you need are 2 eggs, 3 cups of flour, and 3 cups of sugar. But you only have 1 egg. Would you be able to make the full 10 cookies? No. And in this case, the eggs should be considered your limiting reactant. Relating it back to chemistry, a limiting reactant is the reactant that gets consumed first in a chemical reaction, and therefore limiting how much product can be formed. This is a substance that is completely consumed in the completion of a reaction. It is important to determine the limiting reactant because it allows us to complete the theoretical yield of a reaction, in which we also use stoichiometry. The limiting reactant questions are a bit more tricky and a bit more work than the others. The balanced equation C3H8 plus 5O2 produces 3 CO2 plus 4 H2O is given. Determine the limiting reactant if there are 14.8 grams of C3H8 and 3.44 grams of O2. First, we must figure out the masses of C3H8, O2, and the product of choice in where I chose H2O. The mass of C3H8 is 44.094 grams, and O2 is 32, and H2O is 18.016 grams. 14.8 grams of C3H8 given is written first, then for every mole there are 44.094 grams, and for every mole of C3H8 there are 4 moles of H2O, and for every mole of H2O there are 18.016 grams. After calculating all of this, you get the answer that it produces 24.188 grams of H2O. Next, we have to compare that to O2. 3.44 grams of O2. For every mole of O2, there are 32 grams of O2, and for every 5 moles of O2, there are 4 moles of H2O, and for every mole of H2O, there are 18.016 grams of H2O. Calculation shows that there are 1.549 grams of H2O produced, making O2 the limiting reactant. Although it's not the case for every reaction, it cannot be trusted that the smaller amount is always going to be limiting. Stoichiometry must be used to figure it out. Thank you, and you're welcome in advance.